So good morning everybody, and thank you so much for inviting me to your interesting summer school and symposium. I'm an electrical engineer, nobody's perfect, they told me. And I was given the difficult task to give you an idea in only 30 minutes of what an energy researcher or an energy engineer do every day, what are the main frontier topics in modern energy systems, with special focus on computational requirements. It will be necessarily a non-exhaustive overview, also unavoidably driven by my personal experience in some of the research fields we will discuss. Basically, I'm here because in energy systems we have many problems, and sometimes we adopt solutions that you could find very naive or obvious or not at the state of the art. Conversely, you have strong computational skills. In my vision, you have solutions, but you are always looking for new problems, new applications, and new challenges. So that's why I'm here, to try to bridge this gap. The new mantras of energy systems are, first of all, sustainability. You know, environmental, social, economic sustainability. But as you know, the total intersection is dramatically narrow and difficult to be reached. Second, electricity for everybody. While we are here speaking about energy blockchain or peer-to-peer energy local markets, or how to increase the continuity of supply or the quality of supply in our houses, 1.2 billion people all around the world are still without any kind of electricity. 1.2 billion people was the total world population when Thomas Alva Edison invented the light bulb at the end of the 19th century. Then, in many situations, you are not allowed to install new plants, new lines, new power plants. To spend new human, money, or time resources, you have to use better what you already have. That's why optimization is one of the key points of the computational intelligence we require in energy systems. And then, as Marco told us, we are quickly moving from a system with centralized production and intelligence to distributed resources and intelligence. So, in this very short review of calculation and optimization problems, we will discuss about so-called classical problems. Are they already solved? Not exactly, because now we want to reduce computational time, because we want to take decisions not only offline, but also in real time, and not only about the steady-state working points of the system, but also during transit. Then the extension, the complexity of our system is sharply increasing. Just in a single country today, we are speaking about some millions of small producers. We have to handle it. So also classical algorithms could not be adequate anymore. Then we are moving from a deterministic approach to a probabilistic approach, because we have to deal with uncertainties, load, wind, sun, outages, and so on. We want a higher quality of supply, and we want also to optimize many things together. Then we have new challenges. We have to integrate non-programmable renewable energy sources inside our system, theoretically up to 100%, who knows, one day. And when we want to electrify rural areas of developing countries, and in this case, probably the old and wise European model of the end of the 19th century, that top-down approach, generation, transmission, distribution, big is better, is not adequate. In this case, probably you should go smaller with microgrids, then clusters of microgrids, then the interconnection, and in hybrid or renewable. By the way, many things have changed since the last years of the 19th century. At the beginning of the electricity age, loads were lamps, so lighting. Today, when you bring electricity to this new population, the first thing they do is to charge a mobile phone. So we can say that the renewable energy sources, CO2-free economy, and the increase of world energy demand are the three main challenges today. This is the very well-known scheme of a traditional power system with conventional large-scale generation, transmission grids, distribution networks, and final passive users. Looking at conventional large-scale generation, the main research fields with special focus on the most challenges from a computational point of view, are first of all thermodynamics, so the simulation of cycles, not only steady state like in the past, but also during transit, because we want to assess the dynamic maximum performances of our plants. And we also need to set up new 3D or finite element models of many components like boilers, heat exchangers, burners. Then the problem of emissions, clearly. But today, not only classic pollutants like NOx or SOx, but also greenhouse gases, that is global, so CO2. Then, of course, many studies are devoted to increase the energy efficiency, the reliability, the robustness, or the availability of these plants, or to understand what happens with their control systems. The prime mover, so the speed frequency control, and the exciter, so the voltage control, which has also a tremendous impact on the stability of the plant and the risk of blackouts faced to large grid problems. Then we want to increase the flexibility also of conventional plants. Flexibility means reducing their technical minimum or increasing their ramp in percent per minute or megawatt per minute, or to reduce their startup time. And also to assess what size or what kind of technology is more suitable to restart the system after a large blackout. If you go to the transmission grid, for many years a classical computational problem was load flow. Load flow means calculating the active and reactive power flow in each line of a meshed grid. Once you know the impedances of each line, you know the active reactive nodal injection at generation nodes or active reactive consumption at load nodes. Just to give you an idea, this is the mathematical formulation. You can write two nonlinear load flow equations per node. You can have many thousands of nodes in a high voltage grid. The unknowns are active power, reactive power, voltage amplitude, voltage angle. And of course, if you want to calculate 4 n quantities with 2 n equations, you have to impose 2 n quantities, usually P and V at generation nodes and P and Q at load nodes. This was solved already in the past, also for many thousands of nodes by classical techniques like Newton-Raphson or Gauss-Seidel, and more recently also in the perspective of real-time calculation by Stott with the fast decoupled load flow. But today we use load flow equation as the core for an external optimization problem. For example, dispatch the system in order to minimize grid losses. Many other papers today are dealing with the new problem in the idea of use better what you already have, the dynamic thermal rating of overhead lines. So what's the maximum power that a line can carry? Not in general conventional weather conditions, but taking into account the actual present weather conditions that are close to that line. It's a very complicated, both thermal and mechanical problem. We will have a short focus on it later on.
David, what is the average, what is the typical number of nodes?
Oh, if you limit yourself to the high voltage grid, you have some hundreds per country. So at European level, it's some thousands. But now, if you look at the distribution grid, this problem is sharply increasing to millions of nodes. Then other studies, of course, are studying new conductors, high temperature, low sag conductors, or insulated gas cables, or flexible AC transmission system, that is power electronics devoted to reroute on the meshed grid the load flow with respect to what load flow equations say. That's very interesting. And new tools to assess the magnetic and visual impact of power lines or to optimize their maintenance, especially their live maintenance, or while they are in operation. For example, here you see a robot that washes insulator strings when the line is in operation, 400 kVs line. High computational complexity is also in the bulk power system. The bulk power system is the merge of the generation system and of the transmission system. Here the main problems are two: unit commitment and power dispatching. Unit commitment means I want to decide for each hour of the following day which plant must be on or off, and if on, and which produces power, the power dispatching. This problem was already solved in the past by monopolistic public companies at minimum fuel costs, so in vertically integrated systems. And today, in regulated systems, at maximum social wellness that corresponds to crossing the demand and supply price curves, taking into account the grid constraints. This problem is strictly related also to the complex algorithms that are used by our market operators every day and each hour for electricity pricing. So many studies are comparing nodal pricing, zonal pricing, locational marginal pricing. Here you can see a simulation of nodal pricing on a test grid on the real high voltage Italian network, some hundreds nodes. Then we need to size and operate in the right way generation reserve. Of course, we need reserve because we must keep the system in balance, face to contingencies and unexpected deviations of load, sun, wind, and so on. And also we have to simulate what happens just before the blackout to avoid it. So to tune emergency procedures, here you can see the simulation of the use of secondary and tertiary generation reserve and what happens to the system frequency just before a blackout.
So what does just before mean?
Just before?
Take about 5 minutes?
Let me say a couple of minutes. So the first line stops the blackout and it's about some seconds. The second line must act in some minutes. In 2003, Italy went to blackout in 2 minutes and a half. Yeah, but the first go down of the frequency is in some seconds, so it will just be automatic, of course. At the distribution level, power quality means traditionally continuity of supply, voltage supply, but the New Deal are meshed topology with respect to traditional radial topology, and the massive use, massive penetration of ICT for remote monitoring and control. But the real revolution of last years are active distribution networks. So distribution networks with the strong penetration of the generation at the medium and low voltage levels. In this case, the distributor must become from distribution network operator, so lines and loads simply, to distribution system operator, so lines, loads, but also generation and why not energy storage devices. Exactly like the transmission system operator at the upper level, the high voltage level. Renewable energy sources require computational aspects not only for forecasting techniques, but also to assess the hosting capacity of our grids. Hosting capacity is the maximum power that you can install in terms of renewables in a distribution grid without impacting voltage or current constraints. So what's the maximum power that can be accepted by that grid generation side? A grid that was conceived and designed in the past as a passive grid, so a top-down grid, and now it's an active grid with reversible flows. The large use of renewables also entails the bulk power system, so the upper level. Not only because large-scale renewables are directly installed on the transmission level, but also due to the balancing purposes that they pose and the dispatching priority that renewables have with respect to large conventional generation. The load. Loads mean traditionally forecasting techniques. But now, since the generation is not only central and fully predictable, and some generation is stochastic and dispersed, also some load must become controllable. So we are looking for any kind of flexibility, scheduling flexibility and quasi-real-time flexibility. So we speak not only about demand side management, but also about demand response. So quasi-real time, the load must be responsive with respect to price and power signals that are sent by the DSO or by the TSO to the loads. And these loads can begin to provide the system with ancillary services like balancing, reserve, voltage support, defense support, that in the past was provided only by large-scale generation. Of course, at the load side, many studies are devoted to energy saving, to understand what will be the possible behavior of new electricity users, large electricity users, like large fleets of electric vehicles or heat pumps, but also to the optimal operation of prosumers. Prosumers are clusters of producers and consumers, and why not, energy storage devices. Of course, the optimal working point of a prosumer will strictly depend on the tariff scheme, the tariff framework I apply to him. So by driving the tariff scheme, I can change the behavior of people. But it's a social problem, not only a technical problem. What will be their answer, their response? About energy storage, the functions and the position of energy storage devices are strictly related with each other. For example, should I install energy storage devices combined with solar and wind power plants, so renewables, in order to make them more predictable at the transmission level or at the distribution level? Or second, should I install energy storage devices directly on the high voltage transmission grid and operated by the transmission system operator in order to solve grid congestion? Or third option, should I install energy storage devices combined with loads in order to make them more flexible? So what's the best mix, what's the best portfolio of flexibilities? Also taking into account that each function has, in terms of energy capacity and time, I need that, for what I need that service, and each function has its optimal technology that is a good candidate to provide it. Not anything can be provided by batteries. If I want some gigawatt hour, I need, for example, power to gas. I must spend electricity to create hydrogen or methane or something like that and to store the gas. Or for very, very short times, I can use supercaps or flywheels. So batteries are only here, but everybody, when we speak about storage, automatically thinks about batteries. And that's why today so many papers and many academia is dealing with the problem of the optimal sizing and siting of energy storage devices, but also to their optimal operation combined with renewables or loads and so on. Of course, today we are not seeing any equation, formulas, algorithm. We have no time, unfortunately, but I'm giving you just a very short list of papers that could help you to approach some of these topics. Just to have an idea of one of the open challenges, I have a short focus about the optimization of a modern hybrid prosumer or virtual power plant. This can be the boundaries today of a complex industrial customer that has always used the public electricity network to supply its electrical load and a fuel-fired boiler to supply its thermal load. But today he has installed many other things that also links the electricity busbar in black and the thermal busbar in red. For example, the CHP, combined heat and power. I produce both electricity and heat, or I consume electricity in order to obtain low temperature heat. And many other things, electrical storage or thermal storage, that now, thanks to this connection, are also in competition with each other. Or renewables, thermal renewables here, photovoltaic plants, for example, here, or some other electrical renewable in an external point of common coupling if the tariff framework and subsidies make it more profitable. So the first problem here is the optimal operation. Day by day, what's the optimal use of the resources I have already sized and installed? Of course, every day I can only control energy storage devices and dispatchable resources, basically the CHP, the boiler, and the heat pump. This is done taking into account tariffs, selling tariff, buying tariffs, the fuel tariffs, and so on, hour by hour, by minimizing the total operational cost during the day, of course taking into account the technical constraints, the capability of the components, their possible maximum performances, but especially the expected is very important, power profile of renewables and loads. In the past, a very naive technique, but still used in many cheap plants, was not scheduling anything before and going directly to the real time with very simple priority rules. For example, load following is very easy. If renewables produce more or less than the load, I use battery to balance it. When batteries are full or empty or not enough in terms of power, I can switch on the CHP or I can begin to exchange electricity with the main grid. If I'm off grid because I have no distribution grid, I have to keep the system in balance. In some extreme circumstances, I have to curtail the load or the renewables. But of course, today we prefer predictive strategies. So to perform a real optimal scheduling of resources some hours before. Like in the bulk transmission, bulk power system typically is deadhead with some intraday corrections. And this problem, the optimization of this, was already successfully solved in the past by the literature, also by my departments, using mixed integral linear programming. But you know better than me that we can use MIL only if we adopt linear models of our components. So
what is integer?
Integer because you have not only real quantities but also Boolean. For example, on-off of the CHP.
Yes.
Okay. Or you have to change tariff when you are giving electricity to the grid or taking it to it. So you need Boolean variables. And so with MILP you cannot use quadratic terms, for example. So one important frontier topic today is how to optimize all of this, even for more complex schemes, when you adopt more realistic and non-linear models for your components. You take into account, for example, joule power losses, or you consider that the round-trip efficiency of your battery is not constant, and it's strictly dependent on the depth of discharge of the battery. Or, for example, when you want to optimize many things together, not only you want to minimize operational cost, but for example, you want to take into account robustness or reliability, or CO2, or you want to maximize the ratio between what you produce by renewables and what you produce by the internal combustion engines that you would like to be only just a backup source. So the question is, can be really everything related to money? Is it possible to provide just one single cost objective function that takes into account all together, or we want to optimize separate things? That's an important question for us. Then today we want to optimize all of this not under deterministic condition, but under uncertainties. First of all, we don't know exactly what will be the power profiles of load and renewables. And using classical deterministic approaches like MILP, with some ex-post sensitivity analysis about the expected power profiles, is not adequate anymore. So for simple plants, you can use analytical probabilistic methods, but for more complex plants, you need something else. For example, due to our background, we are using Monte Carlo simulations, but of course we need good probability distribution function for the forecasting errors of load and renewables. So we need the statistic analysis before. Other people are proposing, for example, stochastic optimization now in the last years. Then another question is, what time horizon should I optimize? To answer this question, first of all, we have to analyze the periodicity, the classical periodicity of the load and renewables in the site you are analyzing. Also taking into account the edge effects at the beginning and at the end of this time period, especially if the time period is very short. It's clear that if you don't impose that at the end of the day, the state of charge of batteries is no lower than the beginning of the day, the optimizer will use all the energy of the batteries, and you will have batteries empty at the end of the day, and you will have big problems the following day. Then another very popular question. Which software should I use today to optimize all of this? Many people today are programming their own software, for example, in C++. or others are using general purpose optimization packages. MATLAB, but also IBM Simplex, for example. Are they really good? Or in some fields, already some commercial software exists. For example, in the field of prosumers, Homer, but with some limitation, it's not so flexible as we desire. So this is an important question. I would like to have also your opinion about this. Finally, the second problem here is not only the optimal operation, but also the optimal design. So assessing the optimal size in terms of energy and power for each component. So far in power system, this has been traditionally approached as an external loop with respect to the internal optimal operation. I mean, we consider several possible sizing scenarios, and for each size scenario, we optimize the yearly operation of that system, and the size scenario with the best yearly result is our best design for that system. But of course, my question is there something better for the choice of these sizing scenarios to be analyzed, something better than heuristic approaches? For example, now we are using particle swap optimization. Or is it possible also under uncertainties to write a one-shot problem, so an optimization problem that takes into account together optimal sizing and optimal operation on a yearly scale? It's challenging. And finally, today, multi-year approaches mean taking into account also the long-term evolution of load profiles. In the long term, profiles change shape and amplitude, so we have to be ready to calculate different values for the objective function at each year, or possibly changing the optimal size of components during the lifetime of the plant, or also the topology of the grid. For example, one bus bar, two bus bars, and then a microgrid or a cluster of microgrids, and then at the end a total interconnection to the upper national level. Prosumers are very complex, but they are only one leaf of the tree of the smart grid. So today, one very interesting topic is how to analyze and optimize clusters of virtual power plants, taking into account, so each leaf is one of these. Clusters taking into account also network constraints in case of competition or in case of synergy in terms of distribution capacity, and the right to pass through that line of these virtual power plants. My time is finished, but I'm giving you much more materials about two other topics we are dealing with. In particular, the optimal sizing and operation of renewable isolated mini-grids. This is very similar to a full electric virtual power plant, but in this case we are alone. We have no distribution grid, so we have to keep the system in balance, both at scheduling time and in real time. And you will see in the slides I leave you that we are trying, so in this moment, a mix of particle swarm optimization to select the right size scenario to be investigated, Monte Carlo to cope with uncertainties, and MIP to optimize each single deterministic scenario, so 3 inner loops. And finally, the other problem, the dynamic thermal rating, that is very complex mechanical and thermal problem, especially when weather is not certain. Thank you very much for your attention.
Are there any questions?
Please.
Do you simulate what you see, or is it?
Yeah.
What kind of simulation do you use?
For example, for this problem, we are using MILP of Simplex combined with MATLAB. In the past, we were used to program our own software in C++, but now we are using a link between Simplex and MATLAB.
And do you have the data about the load of the grid?
Yes.
Do you them have them available?
Yes, exactly. Especially from the, so the problem here is not only when you are dealing with an industrial customer. Usually he has many years of measures. And if he has not changed his process, his manufacturing process, load is not a problem. But the real problem is when you go to Africa and want to install a new power plant and you don't know anything about that. So we are now post-processing data from old mini grids already installed, but in the logic of big was better. 1 megawatt plant, even if the load is 100 kilowatt, we are processing what the load is doing also in the long term. So that population didn't know electricity. Now, in the long term, they are doing many things with electricity, and the power profile is changing also shape, not only amplitude. So we are taking data, real data from these fields, especially from Kenya and from Uganda. We are reprocessing it, and we are answering the question, what was the best optimal size if in the past we had these tools? And what was, for example, the savings of CO2 in the last 10 years if in the past I have used hybrid mini grids instead of diesel plants? That's interesting. Thank you.
So, okay.
Last question. One of your last slides.
After optimal design?
Yeah, this one.
Yeah.
So here, do you see a centralized optimization, or is each one is optimizing individually? Because you have synchronization effects, because if you all get the same signal, you will synchronize and they won't be optimized.
Yeah. It's still centralized, but not in the sense in the traditional terms of the bulk power system. It's centralized in terms of an aggregator that the distribution level takes into account 3 or 2 or 4 clusters of virtual power plants and optimizes all together. It's clear that the following step is independent agents. But independent agents, of course, will be not in synergy and will be in competition to pass through that line that is not able to pass all the power of everybody.
Do you think it's feasible?
Yes, it's feasible. It's feasible today for, let me say, a low number of virtual power plants, because each power plant is complex in itself. So we solved this problem for some tens of virtual power plants, but probably you would be better than us to solve this problem. In some, let me say, in some minutes. So it's not so adequate for real time, but also it's more for scheduling so far.
What kind of machine do you use for this kind of?
Oh, normal 12 core PC, normal PC. Yeah. It's about some, let me say, here it's about, the only operation is about some tenths of seconds, so it's very easy. But if you have an external loop of optimal sizing, in load following, it's about minutes. If you are going to more, for example, rolling horizon, you need 1 hour. So for design purposes, it's still adequate, but not for real time. Thank you.
Okay, thank you.